Hi everyone, I am Mark Peter Panong, one of the Panong Squared, a third-year mechanical engineering student. In this video, we're going to look at stress transformation and Moore's circle. Let's start by reminding ourselves about the stress element. The stress element is a very useful way of describing the stresses acting at a single point within the body. In this video, we will consider a 2D stress element corresponding to the state of plane stress. The normal stresses and the shear stresses are shown on the four faces of the element. Let's look at a simple example of a beam under axial load. Our stress element is aligned with the direction of the applied load, and so the stress state will be very simple. We will only have a normal stress of sigma x, sigma y, and the shear stresses will be 0. But we might want to rotate our stress element to get the stress state for a specific angle. If there was a weld in our structure, for example, we might want to determine the stresses perpendicular to the weld. Depending on how we choose to orient our stress element, we will get different values for the normal and shear stresses component. We can calculate what the normal and shear stresses will be as we rotate our stress element by using the stress transformation equations. The inputs to these equations are the normal and shear stresses at the starting orientation of our stress element. Moore's circle is a graphical method for easily determining normal and shear stresses without using the stress transformation equations. For problem 7.40, we're going to solve problem 7.18 using Moore's circle. For problem 7.18, the grain of a wooden member forms an angle of 15 with vertical. For the state of stress shown, we're going to determine the in-plane shearing stress parallel to the grain and the normal stress perpendicular to the grain. For our given, we have our normal stress in x, which is equal to negative 3 MPa since the direction is going inward or to the left of our horizontal axis. Next is we have our normal stress in y, which is equal to negative 1.8 MPa since the direction is going downward. Our angle is equal to 15 degree. Note that in using Moore's circle, the angle is double, which the angle becomes 30 degree, and the shearing stress is equal to 0. The very first step in making a Moore's circle is to consider a suitable point O, and through it, we can draw a horizontal line. Next is we're going to plot the points using the given value. Since our shearing stress is equal to 0, we're going to plot the normal stresses horizontally. For our normal stress in x, which is equal to negative 3 megapascal, we can denote it as point A. And for our normal x in y, which is equal to negative 1.8 megapascal, we can denote it as point B. To get the radius of our Moore's circle, we need to get the average of our principal stresses. To calculate the distance of CA, CB is the radius of the Moore's circle. The CA is equal to CB. To calculate the value of the CB by Moore's circle, we can use this formula, which is equal to normal stress in x plus normal stress in y over 2. We need to substitute negative 3 MPa for our normal stress in x and negative 1.8 MPa for our normal stress in y, which is equal to negative 0.6 MPa. Therefore, the radius of our Moore's circle is equal to negative 0.6 MPa. Now with C as center and radius equal to CA or CB, we can now draw the Moore's circle of our stresses. Also, through C, we can now draw a line CD making an angle of 30 degree with CB in a clockwise direction meeting the circle at D. To calculate the average stress, which is equal to OC, or we can use OA plus OB over 2, we can substitute negative 1.8 MPa for OE and negative 3 MPa for OB. Thus, our average stress is equal to negative 2.4 MPa. From our problem, we need to calculate the shearing stress parallel to the grain in plane. For our shearing stress, x prime y prime is equal to r sine 30. So our radius is negative 0.6. Therefore, the shearing stress parallel to the grain in plane is equal to negative 0.3 megapascal. And lastly, to calculate the normal stress perpendicular to the grain, we have the normal stress in x prime is equal to OC plus R cos 30 degree. We need to substitute negative 2.4 MPa for OC and negative 0.6 MPa for our radius. Therefore, the normal stress perpendicular to the grain is equal to negative 2.92 MPa. That's it for today, and thank you for watching.